Welcome, and thank you for attending this session about Synapse Analytics Beyond the Basics. My name is Dennis Torres. I'm a senior software developer working for Ascent Software in Malta. I'm a Microsoft trainer with some Microsoft certifications, and I'm the user group leader of Malta Data Platform User Group. We have a website full of technical content. You would like to visit our website. You are invited to visit our website, and here you can see some contacts, my contacts. Feel free to keep in touch with me through email, LinkedIn, Twitter. You can ask any question, anything. So here are the sponsors of the event. Without these sponsors, this event would not be happening. So thank you for these sponsors. And let's talk about Azure Synapse Analytics. This is not the first session about Synapse Analytics today. There was a session before made by Andrea. He already made a very good overview about Synapse Analytics. I will go a bit deeper on some parts of Synapse Analytics. I will make a small review, quickly and fast review of Synapse Analytics, and then go deeper on some specific parts of Synapse Analytics. So, Synapse Analytics. Synapse Analytics uses the concept of workspace. We create a Synapse Analytics workspace. Inside this workspace, we can create a Spark pool, a SQL pool, or a SQL on demand. So we have three pools that we create inside the Synapse workspace to make different kinds of work. The Spark pool will enable us to query unstructured data. The SQL pool will enable us to query structured data. And the SQL on-demand pool, besides the fact that it's on-demand, it means that we will only be charged by the queries we'll make against it. There is the fact that the SQL on-demand pool is able to query both structured and unstructured data. Synapse Analytics has the Synapse Analytics Studio. It's a powerful web tool which integrates all the features of Synapse Analytics. On Synapse Analytics Studio, we can access these pools, we can query over these pools, and we also can access data integration tools. In this case, data integration tools, I'm talking about Data Factory. We can use Data Factory in a way like inside Synapse Analytics from one single tool, which is Synapse Analytics Studio. So we can use Data Factory from this tool, and we can also use Power BI on this tool. We can link a workspace from Power BI with Synapse Analytics and visualize the data that are in our pools, Spark pool or SQL pool or our storage. So we can use Synapse Analytics to manage all the spectrum of a warehouse process. Let's see, we have the ingest part of the process using Data Factory. And we are not replacing technologies that just arrived some years ago by new technology. We are not replacing technologies. There are an integration of technologies. So Synapse Analytics can be data factory can be used inside Synapse Analytics from the same tool. Then we have the store and the process managed by the pools. The pools are able to store and process data. And finally, we have the visualization of the data using Power BI. Everything integrated in a single tool. The idea was that it was quite difficult to have professionals to manage each one of these different tools and make things work together. So Microsoft is integrating these tools, these features, in a single tool that you have access to all of them. That's Synapse Analytics. That's the idea of Synapse Analytics. And we can access structured data using Synapse Analytics, unstructured data using Synapse Analytics, and big data using Synapse Analytics. We can access all our sets of data, structured, unstructured, or big data. It will work for all of them. Here's some screen captures from the Azure portal. So we can see here the pools. I created a workspace of Synapse Analytics with two pools, one SQL pool and one Spark pool. Although there are not only two pools, there are three pools. The point is that the SQL on demand doesn't appear together the other two. So we have also a SQL on demand available. So we have the three features available inside this workspace. I made the three features available inside this workspace. And this is the main screen of Synapse Analytics in Azure portal. This is the main script of Synapse Studio on the main portal. From the analytics, you open Synapse Studio, and in Synapse Studio, you can create SQL scripts, notebooks, which can be SQL notebooks or Spark notebooks, and you can create data flows for data ingestion using Data Factory technology. You can create Spark job definitions and pipelines for data ingestion, also using Data Factory technology. There are some demonstrations about this on the previous session as well. I'm just highlighting how these tools, different tools that were difficult to manage before, in a way that you would need a different professional to take care of each one of these different tools. Now you can manage all of them together inside Synapse. And we have here at the side the visualize option. I can link a Power BI workspace with Synapse Analytics. The features are not totally complete yet. For example, last year I was at PES Summit and I saw this demonstration and I had the opportunity to ask some questions to the people responsible for the product. And I asked, for example, will I be able to create a Power BI data flow from the Synapse Analytics interface? No, not yet. So it's not complete, but it will evolve. So let's focus on the SQL pool. What's the SQL pool? As you are seeing on the image, SQL pool is the evolution of Azure SQL Data Warehouse. There is a big misconception in the market that SQL Data Warehouse was renamed to become Synapse Analytics. It was not. It was not. Synapse Analytics is a bigger product than SQL Data Warehouse. It's bigger than SQL Data Warehouse. SQL Data Warehouse is the SQL pool inside Synapse Analytics. Synapse is bigger than SQL Data Warehouse. So in Synapse, we have these three pools: Spark, SQL Pool, and SQL On Demand. The point is that these three pools are covering a new word that is called data lakehouse. The word data lakehouse is appearing a lot in the market to make reference to Synapse Analytics. What this means is a mix of data warehouse and data lake. And the meaning of this mix is the idea of having access to structured and unstructured data at the same time. So on the same tool, I mean, and link them and merge them. What you need to do is then you can access structured and unstructured data at the same time. Well, I'm quite old in the market. I started to study data warehouse many years ago. So I'm not a fan of this word. I don't like too much this word about SQL, about data lake house. I don't like too much this word. Why I don't like this word? Because I'm old. And when I started studying data warehouse, the definition of the data warehouse already included structured and unstructured data. The data warehouse, by definition, includes unstructured data. So we would not need a new tool, a new word, I mean, not tool, a new word to define that. That's the data warehouse on its maximum, including structured and unstructured data. The point is that we have been missing tools to work with unstructured data for so long that we get used to call a data warehouse only the structured part. When seeing technical sessions, when reading technical articles, and having touch to technical content, using many places the data warehouse being used as the definition only of the structured part, not the unstructured part. When on its origin, on its source, it was both. The warehouse was created to include both structured and unstructured. It's an interesting question about definitions and names. Okay. What's wrong with Azure SQL Data Warehouse? What I mean about that? I mean that SQL Data Warehouse is somehow disappearing, or we can see disappearing, or we can talk, say, changing name, and we will not talk about SQL Data Warehouse anymore. We will talk about SQL pools inside Synapse Analytics, because SQL Data Warehouse became SQL pools inside Synapse Analytics. One piece inside the Synapse Analytics. So this explanation can make it very clear how the idea that the SQL Data Warehouse was only renamed to Synapse is wrong. Synapse is way a bigger product. SQL Data Warehouse was renamed to a SQL pool. A SQL pool which works inside Synapse Analytics. But what's wrong with Azure SQL Data Warehouse, which led to this name changing and this transformation? The problem is the name. The name, Azure SQL Data Warehouse. This is a problem because the name of the product is the name of a concept, data warehouse. And this creates a lot of misconceptions. When you create a product, name it against a concept, you create a lot of misconception. The point is, you don't need Azure SQL Data Warehouse in order to make a data warehouse. That's the main point. You don't need Azure SQL Data Warehouse in order to make a data warehouse. If you think about the structure part of the data warehouse, you can build the structure part of the data warehouse in a SQL DB, in a SQL managed instance. There is nothing preventing you to do that. There is nothing preventing you to build the structure part inside a simple SQL DB or a simple managed instance. There is no problem with that. What happens is that some data warehouse are very big and they can't be put inside the SQL DB or managed instance because it would not support them. They are very big. That's when you need to go to Azure SQL Data Warehouse for big, giant data warehouses, not a small thing. A small thing has not the need to be included inside Synapse Analytics, inside SQL pools. Why? Because the main behavior, the main point of this product, which was called before Azure SQL Data Warehouse, is to be an MPP, Massive Parallel Processing Solution. This is the main focus of this product, to be an MPP. So you may need it for very big data warehouses. If you put a very small data warehouse model inside an MPP environment, you are paying a lot of money for something that you are not really in need, that will not be really useful for you. You could achieve the same result in a smaller environment like SQL DB or managed instance with no problem. So the SQL pools, which are the new SQL Data Warehouse, are for big data warehouse, giant big data warehouse, because they are focused on MPP processing. This leads to another point. You mentioned this point now. The point is, this is not something like, let's say, plug and play. If you are thinking about something plug and play, forget it. It's not plug and play. There are many fundamental configurations to make the environment work well for you. If you think about something plug and play, when I'm saying plug and play, I'm saying, oh, create an instance, import your tables there, and that's it, it's working. No. It will give you the worst result possible. And in this case, you'll be disappointed and you end up creating fake news around the web saying the product doesn't work so well and so on. And the web will be full of fake news because you haven't used the product correctly. So one purpose of this presentation is to highlight how this product is not something plug and play. It's not something like SQL database or managed instance that you can put the tables there and you have even an analysis to define the best index for you. Not this product. It's different. So the name led many people to use a product that they were not in need, and this is due to an historical naming problem. And this is an example of the historical naming problem. America is the name of the continent discovered many years ago. The entire continent is called America. That country in the middle of North America is called United States. But they like to call their country as America, as if they were the only single country inside the American continent. That's a historical naming problem. And this happens with products as well, as the example I just gave about SQL Data Warehouse. That's it. So let's talk about the SQL pool. Note that I'm already calling SQL pool MPP architecture. How this MPP architecture works. And in fact, you already saw this on the previous presentation. I'm repeating a bit. So we have a control node. Control node. Let's translate this. What's this? Do I have one server? Do I have many servers? I will illustrate very clearly that there is a huge difference between the logical view of what you put inside the SQL pool and the physical view of what you put inside the SQL pool. There is a huge difference between both. So we have a control node. The control node is responsible to receive the queries. It's a computer. Yes, it's a computer, virtual machine somewhere. Yes, it's a compute node. And you a control node, sorry. And you have many compute nodes. And the secret here is that the data itself, represented here by this DMS image, is broke among the many compute nodes we have. So the data is all broke among many compute nodes. So the control node receives a query, will process the query. What the control node will do? Will break the query among all the compute nodes. All the compute nodes will process part of the data for that query, the data which was with them. So each compute node will make this processing and will return the result of this processing to the control node, which will map the result together and give us a single result. So that's the process on an MPP architecture. The query is broke among many compute nodes. Each compute node has access for part of the data, to part of the data, and each compute node will generate its result. The result will give back to the control node, and the result will be united, and we'll see a unique result. And the resemblance with mapping result may not be only a coincidence. Let's say this is kind of I could say MapReduce implementation by Microsoft, but just not following MapReduce. It was implemented to be used with SQL. It was implemented to use SQL architecture. It's using a pattern for MPP architecture with SQL technologies. So we will create a SQL pool. When we create a SQL pool, we define the performance level of the SQL pool, which you are seeing here on the left column. These, let's say, codes are the performance level of the SQL pool. Then you have the number of compute level brings for you. So you choose a performance level in order to choose how many compute nodes you would like to have. So from 100 to 500, you have only one compute node. Only one single compute node. So it's used more for demonstration. Poor speakers like me that can't afford the bigger performance level, which would get all my money and break all my credit cards. We make demonstrations using a low performance level like a DW100 with a single compute node, and that's it. That's it. But in order for in production you really feel the benefits of a SQL pool, you need to choose a higher performance level, starting from 1000 until 15,000. You need to choose a higher performance level, which will bring to you many compute nodes. And we already talked before on the previous slide, we mentioned how each compute node has a piece of our data. Each compute node has part of our data. How is this distributed? The point is the distribution is fixed. I mean fixed in terms of in the quantity of the distribution. Our data is broken in 60 pieces. Our 60 pieces, and that's it. Our data will have ours 60 parts. The point is, according to the number of computer nodes that we have, the distributions of data will be broken among the compute nodes. For example, on the lower performance levels, all the 60 distributions are in a single compute node. One guy will need to process everything. We are not really using the MPP in this case, it's just a demonstration. You are not really using the MPP in this case. But when you go forward, then with DW1000, you have 30 distributions per compute node because you have two compute nodes. So the 60 distributions are broken among the two compute nodes, and so on until DW15,000, where you have 30 compute nodes, and you have only 2 data distributions for each compute node. Only 2 data distributions for compute node. And as you will note in further example, we need to control this quite well. And there is also a difference of memory available according to the performance level. Microsoft provides a different amount of memory for each performance level. Okay, this is an example of the distribution. Our table will be distributed among compute nodes. And this distribution is made according some kind of calculation. Some kind of calculation over the table needs to be used to make this distribution. It's a distribution function which makes this calculation. And we have 3 distribution methods, distribution functions to make this calculation. We have the round robin, which is the full distribution method. The full distribution method, I repeat, the full. It means that if you use the plug and play technique and just put your tables there and let's see if it works, you are using the round robin distribution. Let's see how bad it is. Then we have the hash distribution. The hash distribution is used when, according your data, when you have a column which you would like to distribute among the compute nodes. For example, date. You can distribute dates among the compute nodes. The distribution can be related to many different keys, and you need to choose a key that will ensure an even distribution among the compute nodes and will benefit the queries, in order that some queries may need access only to a few compute nodes. We will not use all of them to make the processing. If you distributed your data randomly among the compute nodes, all your queries will need to use all your compute nodes to find your data. That's a problem. If you use a more planned distribution, some queries may need to use only a few compute nodes to get the result. And the third data distribution technique is the replicated technique. This means that our data will be replicated among the compute nodes. We will have a total copy of our table with each compute node. So when should we use each of these techniques? Well, to understand when we should use each of these techniques, we need to analyze the logical part of this structure. What's the logical part of this structure? It's a star schema. We are talking about data warehouse. It's a giant data warehouse, but it's a data warehouse. And being a data warehouse, it's a star schema. This slide was well stolen from Andrea. This slide was on Andrea's presentation this morning. He authorized me to use this slide. This is very good here. So yes, we are talking about the same thing. I'm talking about the distribution, and he explained it, a good pattern to make these distributions. how is this a good pattern? In a star schema, we have a fact table rounded by many dimensions table. The fact table usually is the biggest table that we have. The biggest table that we have is the fact table, and is the table where all our processing will be concentrated, because we need answers related to the fact. For example, the fact can be sales, like this example, sales fact. We need answers about sales. So most of our queries will be concentrated in making processing over the fact table, over sales. While the dimension tables are smaller, related to the fact table, and will always be used, may always be used in processing as additional data to illustrate our queries. We'll need to see sales by product, by date, by store, by customer. So we need to see sales, but we need to see sales according to different dimensions. So what's the best distribution functions for this? The best distribution functions in this case would be the sales fact, which is the biggest table. We use the distributed function as a hash distribution. So we need to choose a key, a good key. Date sometimes is a good key, but it depends a lot on your model. Don't read the pattern and follow it. It depends on your model. The purpose here is to choose a distribution key that makes an even distribution among the compute nodes in relation to the amount of records. You need to choose a correct key to make that. But and about the dimensions. After you distributed the sales fact, you have no idea which dimension records the sales fact on each compute node will need, because you distributed based on one key of the sales fact. But what dimension data do you need? They may need many different dimension data, and it may happen that different compute nodes may need the same dimension data. If I'm calculating my information by date, for example, the amount of sales by date, this compute node has some dates, this compute node have another set of dates, but among each set of dates, I may have relation to all the products. So what's the best replication technique for the dimensions replicated? So a good practice is to use hash for the fact table and use replicated for the dimension tables. That's a good practice. Now you may be noticing, well, but the default was round robin. Yeah, the default was round robin. That's what I'm saying to you. This is not a plug and play software. If you don't know about the distributions, if you don't know about the distribution techniques, about the compute nodes, about these techniques, how MPP works, you will just create tables there, try to get some result, and will be disappointed with the results you get. You'll be disappointed. So let's see a demonstration. So I'm using here SQL Management Studio. I'm using SQL Management Studio to connect to my database. You have a surprise soon about this database, but let's say this is a database on my SQL pool, and I have many different tables on this database. Inside my SQL pool, I have many different tables here. Let me open the Solution Explorer. Sorry, I think I'm on the wrong window. Yeah, sorry, I'm the wrong window here. I have it already open. Okay, Solution Explorer. Here. I will drop this table test just to start. Delete. And I start with the first demo. Okay, I'm connected to new SQL pool, so I'll create the table test. There will be a lot of surprise here. For example, the primary key usually is non-clustered, and keys are not enforced here. We set a primary key, but the key is not enforced in this MPP environment. So I'm creating the table test and feel like I'm using the default, like I'm a newbie on this area. I'm using the default, and let's see what happens. What I'm losing here, I'm losing the opportunity to set the distribution of the table together the create table. This should be set together the create table, the distribution that will be used. And since I haven't chosen a distribution, which distribution was chosen for me? Which distribution was really chosen for me? Let's check. I can use queries over system tables, and we have totally different system tables to check the distributions. So I have here a table called PDW, table distribution properties. I challenge you to remember what PDW stands for and answer in the chat. It's a challenge because it's quite interesting how this technology evolved from some quite old technology that existed, I should say 10 years ago. This already existed. Yes, this already existed about 10 years ago. And this evolved from quite old technologies, but it's completely different. So I'm joining this object and this schema to get the information about the distribution. So let's execute this query. Since I have many tables, I'm seeing the distribution for all the tables that I have. I have some tables using round robin, and the test table that I just created is using round robin. My test table is using round robin distribution. I have some tables using replicate distribution, and I have one table using hash distribution. Okay. Let's check other information about these distributions. How can we see something more about these distributions? We have another system table called, sorry, PDW nodes table. This will allow me to see the physical tables existing inside our MPP environment. And the physical tables are these tables with very strange names. Oh, we haven't created these tables. We haven't created this. Where has this come from? That's the point. Let's start to accept that what we are seeing here is not the physical structure of the SQL pool. The physical structure is it's not hidden. We can read it, but it's not exposed directly to us. We work in the MPP environment using a logical structure, not directly the physical structure. So all these tables are the physical structure created on my PDW environment, on my MPP environment. I can use another system table, syspdw table mappings, in order to discover the relation between these physical tables with the logic tables. So I'm querying this, and we can see the relation between the physical tables and the logical tables. Okay, we are seeing that there is a big difference between the logical model and the physical model. But what we will achieve by knowing this physical difference? The point is, we need to understand how our data is distributed among the compute nodes. If you make a bad distribution of our data among the compute nodes, things will not work well. We will not get from the SQL pool the benefit that we were expecting. And that's a problem. So we need to understand how this logical structure maps to the physical structure, so we can verify how the data is distributed and change the distribution if needed. So here I filter the table mappings by a single table. Let's say see a distribution of a single table, the table test. So here I have a single table. I'm seeing the distribution of a single table test. Let me adjust here the zoom to highlight something for you. Here, 60 rows. Why there are 60 rows? Because we have fixed distributions, it's a fixed number. Each table will be broken in 60 distributions. So each distribution is a physical table. So our logical table will be mapped on 60 physical tables, which are called distributions. That's it. So now we are better understanding the concept of distribution in the middle of the technology that we are used to work with. So let's see the physical nodes, the physical database in this case. With this query over PDW nodes, PDW physical database, I'm showing to you that the 60 distributions are not only a matter of different tables. The 60 distributions are broke in 60 different databases. In the end, each distribution could be in a different server. So each distribution is broke in different database, and this database contains the table for the distributions. In fact, each distribution has two databases, the main database and one for cache data. So let's join information together and see how the tables are distributed. Let's filter specifically by the test table that I created. So as a result of this query, I see the logical name of the table. I selected only one. The physical name of one of the distributions, in which PDW node ID this distribution is, and the distribution ID, the ID of the distribution. Of course, all PDW nodes IDs are the same because I'm a very poor speaker who is using the W100 for the demonstration. So we have only a single compute node. I can see this, can try to see the same information for the trip table. But the problem here to see this information for the trip table is that I have more than a single trip table. I have a trip table on schema DBO and a trip table on schema HSH. So I would need to improve this query in order to be able to see all the information about the trip table on the other schema. So I need to check the schema of the filter table. I need to filter by the schema. In fact, the previous query, this query where I was not filtering by the schema, this query gave me a very strange result because once executed, it gave me 120 records as a result. Why this gave me 120 records as a result? Because I have two trip tables and I haven't specified the schema. So it got the information from the both trip tables without specifying the schema. That's why. Okay. So we saw about the schema. Let's go one step further. What if I would like to see the number of records that I have on each distribution? I would like to see the number of records on each distribution. Well, let's get back to our test table. You saw that I created a primary key that was non-clustered and non-enforced. This was some of the difference when creating a table here. But another difference is that the full configuration for the table is to have a clustered column store index. This MPP environment SQL pool is focused on column store index for the storage and queries and performance queries. You are on an analytics environment, and column store was made for analytics environment. This makes all sense. And Now I will need to remember you about the concept of column store index. Column store index, when created, they break the data in whole groups. So each column store index has many whole groups, and each whole group has a total of 1 million records, more or less a bit more than 1 million records. And when the row group gets to this total, is fixed on 1 million records, the row group is compressed, and this will make the performance better. Open row groups are waiting for more records, and they are not compressed yet. So, why am I explaining all of this? I'm explaining all of this because in order to get the number of records that we have on each distribution, we need to read the number of records we have on each row group and identify on which distribution is each row group. So another big query that will be available on SQL Saturday website. And just after this session, I will make all the queries available on SQL Saturday website. So here we can see the table.
Dennis,
Yes.
just a second, 10 minutes.
10 minutes, okay. So we have here the table name, the distribution ID, PW node, PDW node is the same, and the row group ID. It happens that we may have more than a single row group for each table, especially the trip table, because the trip table is the fact table. So we will have more than a single row group for each table. And we can see the amount of records on each row group and if the row group is compressed or open. This is important to manage the row groups. Maybe ask for a reindexing at some point. It would be recreate the cluster column store index and analyze if we shows the correct field as a hash distribution for our table. If we choose the wrong field, we would have uneven distribution among the nodes, and this will create problems for query performance. Here I have queries testing the whole groups for many different tables. Here for tripping hash, I first tested trip in round robin. Tripping hash is a bit different because in this case it aggregates the data according the dates. It broke the dates according one hash and aggregated them according these dates. So in the end, I have open whole groups on each compute node, on each distribution, because I have only one compute node. So we have open segment here, but that's not exactly a problem because our data is more concentrated. If I make a query filtering by data, the reading result for each compute node will be way smaller. Okay, I have queries here to check this for other tables, and I have here a view to check column store density. I created this view. This view is on the file demo2. Is a view getting many information from the system tables in order to analyze the density of this column store index. How is the distribution of the rows on this column store index? So I can see my tables. I can see my tables, the schema, table name, and how is the distribution, whole count, total for the tables. And I have here max whole count per distribution, the maximum whole count per distribution, and the number of whole groups per distribution. Mind that the only table which needed more than a single whole group per distribution was the trip table, because it's the fact table and it's usually bigger, way bigger than the dimensions table, so it needed more whole groups per distribution. Okay, before continuing with this demonstration, let's get back to our slide quickly. Let's talk about resource classes. This is another thing that highlights a lot how these environments, SQL pools, 4 minutes, right?
Yeah, no, 5. We have also to give space to the attendees to ask if they want to ask any question. So I think
Okay.
if you can move to the end,
Okay,
the conclusion.
I will go fast on this just to summarize this.
Okay.
Resource classes, what's this? Resource classes control the resource used for each user. They can be static or dynamic. This means the user will always use the same amount of resources, or the resources can be dynamic. It can change according to the query the user is making. And these are database rows. And this is the highlights. The administrator use always the smallest resource class possible. So the administration has the worst performance possible. So the first thing that we need to do is to create a user with a better resource class. Like here. Here we see the distribution of resources among the resource classes. In this case, memory allocation for resource classes. So we need to create users allocated to different resource classes. And this allocation to different resource classes needs to be according the queries that will be made. For example, the import process may use a user with different resource class, with a smaller resource class, because it can take longer, while more important queries would use bigger resource classes. So resource classes is another configuration essential for this environment, and the environment starts with the administrator using the smallest resource class possible. So let me skip a bit. Sorry for that. Thank you very much for being on this session. Thank you very much for attending this session. And I hope have achieved the main purpose of this session, is to highlight some deeper technical details on the SQL pool, which before were SQL Data Warehouse, illustrating that this is not a plug and play tool. You need really to make a good management over what is being ingested inside the tool. It's not difficult, but it's not plug and play. Thank you very much.